Hello and welcome to Still Behind the Bench. My name is Adam, and on this channel I will attempt to describe the science behind distilling spirits in a more technical way. Hopefully it'll whet your appetite to learn more and teach you enough so that you're more self-sufficient. So for this video, I'm going to be talking about buffers. Let's get started. So what is a buffer? What is it used for? How does it work? A buffer is a composition of chemicals, namely a weak acid and its conjugate base, or a weak base and its conjugate acid. It's used to keep the pH of a solution at a fixed value or as close as possible by neutralizing any added acid or base. To understand how it works, we have to go back to understanding what a weak acid or base is, how they act in water, and how their conjugates act. I'm going to focus on weak acids and their conjugate bases since we are always going to want to have the pH under 7 in acidic territory. So a strong acid is a compound when put in water, it completely dissociates. So every molecule of hydrochloric acid, HCl, will dissociate into a hydrogen ion and a chloride ion. So if you put 1 mole of hydrochloric acid into water, you'll have 1 mole of hydrogen ions and 1 mole of chloride ions, since they're in equal proportions in the hydrochloric acid molecule. But when it comes to a weak acid, only some of it will dissociate. How much dissociates is based on a value called Ka, which represents the acid dissociation constant. The conjugate base of that weak acid will dissociate the same amount as the weak acid, since it's a salt that is the result of a reaction of that weak acid and some other base. So an example of a weak acid and its conjugate base is citric acid and sodium citrate. This sodium citrate could have been created by a reaction of the citric acid with a base like sodium hydroxide. So this weak acid will dissociate some amount, releasing hydrogen ions. When those hydrogen ions react with an introduced base that is attempting to raise the pH, they will neutralize that base. And when that happens, more weak acid will dissociate until this dissociation constant is fulfilled. The conjugate base does the same thing, but it will be neutralizing any added acids. So there are some rules that we should be following when we are choosing which weak acid we are going to use for our buffer. Only plan on the weak acid being effective within 1 pH point of the pKa value. And the pKa is just the negative log of the Ka. We'll get to that in a bit. So if your pKa value is 4, if you tune your buffer for a pH of 3 or 5, it'll only be about 80% effective. If you're 1 pH point away from the pKa. At 1.5 pH points, it's only about 33% effective. And then at 2, and then at 2 pH points, it's only about 10% effective. When a weak acid has multiple pKa values, like citric acid does, and those different pKa values are all within 2 pH points of each other, which they are with citric acid, you can consider the entire range from the lowest to the highest as the buffer's range. But it's still ideal to choose the pKa closest to your intended pH. Buffers are strongest when the concentration of weak acid is the same as the concentration of conjugate base. So if you were putting in 0.01 moles of an acid, you'd want to put in 0.01 moles or as close as possible of your base. They are the strongest at this point. If possible, I guess the last rule will be, if possible, adjust the pH using a strong acid or a strong base. You can do it before or after adding the buffer. I typically do it before. So I might put a bit of hydrochloric acid, or I use hydrochloric acid or sodium hydroxide to adjust my pH up and down before adding buffer. You can find this at most hardware stores. Sometimes it's called muriatic acid. Let's see. Muriatic acid. And then NaOH is just lye. Yeah, I think you can find sodium hydroxide on Amazon as well. As far as I know, you can't find hydrochloric acid on Amazon, but maybe they sell it in your area. But yeah, a lot of hardware stores sell this as muriatic acid. Sometimes for adjusting pool pH, sometimes for acid washing concrete before doing a coating on it. And yeah, I got mine at Home Depot. So next up is deciding which weak acid and possible conjugate base you want to use. I made this list, link in the description, and it's essentially what I use. There are 6 acids on it, weak acids: citric acid, lactic acid, ascorbic acid, which is vitamin C, acetic acid, vinegar, tartaric acid, and malic acid. So it shows a bunch of weak acids, a bunch of different possible conjugate bases, shows their molecular masses, solubilities. It also shows the various pKa values, as well as their Ka values. You can see for citric acid, there are multiple Ka and pKa values. That's because it's called a triprotic acid. Solubility is at 20 degrees Celsius. I don't think we'll ever run into solubility issues. Most of these are way higher than any amount we would probably ever add, but it's good to know. So in order to know what concentration of weak acid or conjugate base we're going to want to add to or make our buffer from, we need to know what the potential concentration of acid or base could be added that we're trying to combat. I typically aim for a potential drop in pH to 3.0. I have never really had it go below 3.0. Most washes typically don't get lower than that, although I have read cases going down as far as 2.5. If you want to protect against pHs that go that low, you can. So all we need to do is figure out the concentration of hydrogen ions that would be added going from our intended pH to a pH of 3.0. So the pH I'm going to plan for is 4.8. And the potential drop is 3.0. So the math is pretty simple. I'm pretty sure I've already shown it in my pH and adjusting pH videos, but I'll do it again here. So the concentration of hydrogen ions being added would be equal to 10 to the negative 3 plus 10 to the negative 4.8. That equals 0.84 moles per liter. Or you could just say 0.001 moles per liter. It's a pretty small number. But a general rule you can go by is that when you make your buffer, make it 10 times over the presumptive amount of hydrogen ions that could be added. So we would want to put in 0.01, or the concentration for our buffer, we would want to be at 0.01. If you went down to a pH of 2.5 instead, this value would be 0.003. And so this would only be about 3 times as high. It would probably still work, but I would suggest going up to a 0.03 mole per liter. So let's figure out how much of our weak acid and conjugate base we need to add. So there's a common equation taught to students to use to figure out how much or how much weak acid, conjugate base, or weak base and conjugate acid. It is called the Henderson-Hasselbalch equation. And the equation goes like this. pH equals pKa plus the log of the concentration of our conjugate base over the concentration of our weak acid. We already know what the pH is going to be. We want a pH of 4.8. We know what the pKa is because we can just look at the list I created, or you can always just look up the pKa value of whatever you choose, or the Ka value. So I'll show you from the beginning if you only know the Ka value. pKa equals negative log, and this is log 10, just so you know. Negative log of, and I'm going to use citric acid. I'm going to use its second Ka value. 1.738 times 10 to the negative 5. And then when you get done doing all this math here, you get a value of 4.76. Well, that's the second pKa value for citric acid. So we can put in 4.76 plus log, and again, this is log 10. If you're going to be using Wolfram Alpha to help you do the math, make sure to write log 10 and then your bracket, because if you just write log on its own like this, it'll think you're taking the natural logarithm, which the number is pretty close, but it's not the right value. So we don't know what our base amount is going to be, but we know the concentration of our acid is going to be 0.01 moles per liter. So first step, we'll move that over. That becomes 0.04. Then to get rid of the log, you do the x to the power of 10 equals x over 0.01. Then we get 1.0965, and we're going to multiply them both by 0.01. So we get x equals 0.01965 moles per liter. So this is in moles, but that's not a very easy to use number. So we're going to switch that over to mass using another simple formula. Alright, so I've decided I'm going to do this next part in a different color just so it's easier to see. There's a very simple math triangle that we use in chemistry. Essentially, it's grams, moles, and molecular mass. Looks like this. So molecular mass is grams per mole. Citric acid has a molecular mass of 210.140 grams per mole. Sodium citrate, the molecular mass is 258.06 grams per mole. So all we do is we multiply this number and this number by the citric acid molecular mass and sodium citrate molecular mass. So our citric acid mass is 210.140 grams per mole times 0.01 moles per liter, and that equals 2.10 grams. Easy. And then sodium citrate mass, 258.06 grams per mole times 0.01965 moles, and that equals 2.83 grams. So this is how much citric acid you'd add, this is how much sodium citrate you'd add, and this is per liter. So if you wanted to add to, say, 5 gallons of liquid or 19 liters of liquid, you'd just multiply this and this by 19. So you'd get probably around 40 grams citric acid, and what would that be? Almost 60 grams of sodium citrate to make this buffer. And so the math, you can see the math isn't all that difficult, especially if you're going to use Wolfram Alpha. You can essentially type this out and make sure when you're typing it out into Wolfram Alpha, you got to remember to have that 10 in there, so it knows you're doing log 10, and it'll just give you the value of x. And yeah, let's just get rid of the per liter there, just moles. 1 mole per liter is essentially just 1 mole in 1 liter. So yeah, you type it in like this, and it'll give you this value down here, or something similar to it. All right, so the last thing I wanted to show was what could be the pH changes with our buffer if certain amounts were added. So originally we calculated, or I calculated, that if we dropped to a pH of 3, that would be like adding 0.001 moles of an acid of some sort. So I'm going to show you what the pH would drop to if you did that, as well as if you added the same amount of acid that we added as our weak acid. Then I'm going to show the same thing as if we added a base. So this first one is we've added 0.001 moles of base. Our pH would only rise from 4.8 to 4.84. Pretty good. If we added the same amount of base as we added conjugate base, it would still only rise to a pH of 5.04 from a 4.8. Then, if the amount of acid that we were expecting to be added was added by, say, a yeast or a lactic acid producing bacteria or an acetic acid producing bacteria, our pH would still only drop to 4.758 from 4.8. So that's still a tiny amount. And then if for some reason we had the same amount of acid added that we added in citric acid, our pH would still only drop to 4.5 from 4.8. So you can see buffers are pretty strong, and they do what they do well when you've followed the rules or the guidelines, rules of thumb, whatever you want to call them, staying within 1 pH point of the pKa value is probably the most important rule to follow. And then having roughly the same amount of weak acid and conjugate base and weak acid. And yes, okay, so now I'm going to show you a simple example with a citric acid buffer. It won't be 4.76 because my scale is not calibrated. It's just a cheap jeweler's scale like this. You've probably seen it in my past videos. It's not the most accurate or precise thing on the market, but it works well enough for this example. All right, so let's go take a look at that. All right, so here we are behind the bench. I have this little experiment set up. In this flask here, I have a citrate buffer, citric acid and sodium citrate. In this flask, I have distilled water with some calcium carbonate mixed in. And then this is just distilled water that I use to wash the probe off. Over here, I have 3 graduated cylinders filled with 5 milliliters of just regular table vinegar. I think it's 5% acetic acid. Essentially, all I'm going to do is show you when I dump in 5 milliliters of acetic acid into the buffer, into the alkaline water, and then I'm also going to do just this washing flask, which is just distilled water, to show you what kind of change you'll see with a buffer and without a buffer. All right, so you can see the citrate buffer has the solution at 4.43. So let's see what happens when I add some vinegar. Give this a little stir. Drop down to 4.31. Not too bad. This is an amount of vinegar that if it was in your wash, you would definitely smell it and you would know that you have a Acetobacter or Gluconobacter infection. So let's wash this off and we will try the next one. So here we have, last time I measured it was 7 point something. Seven 7.21, 22, 3, stabilize. I imagine it'll probably stabilize around 7.3, but let's just see what happens when we add this vinegar. Whoa! Look how far that dropped. It's climbing back up, but we went from 7.3 to 4 point something. It was a huge drop. Remember, with this, it dropped from 4.43 to about 4.31. This is a significant drop. This was 2.3 something points, pH points. So let's see what happens with just our regular water. So it's around 4.98 it was sitting at before. Close to 5. So we'll add in that 5 milliliters of acetic acid. Now, it might not seem like it was a huge change. I mean, it only dropped about a little over 1.5 points, but that's because distilled water can't be read very well by pH meters because it doesn't have very many ions in it. Because I'll show you. Mode. You can see a pH meter is, in effect, actually reading a voltage level. This is 216 millivolts right now. So if there aren't enough ions for the probe to read it properly, then it'll give all kinds of weird answers. So I wouldn't really trust what this says, but it's just an example of the pH dropping. So in the unbuffered water, we had a little over a 2.5 drop. And in the buffered, we only had a 0.08 point drop. That just shows you how well buffers work in keeping the pH around the value that you want it to be sitting at. All right, and that's it for buffers. I hope you learned something. Please click like and subscribe if you want to see more videos like it, and have a good week.